Okay, so let's talk about the scientific method here a little bit. Obviously, we have 6 different parts to the scientific method. Really, parts 2 and 3 are pretty much the same thing, but for the most part, we'd like to separate those because they do have their own functions, so we do separate them. Okay, first of all, obviously, you're going to make an observation, which really will help you pose a question. We're going to answer that question with a hypothesis. We'll get into each one of these terms as we go along here. We'll make predictions based on those hypotheses. And the predictions responsibility really is to test the hypothesis. Okay. Then, of course, you'll conduct a controlled experiment. That controlled experiment will test the one experimental variable that you want to try based on your hypothesis. It should, of course, get some data from your experiment. So eventually we will analyze that data. After we've analyzed that data, we will come to a conclusion whether our hypothesis was correct or whether it was incorrect. And really, hypotheses are really only meant to be disproven. They're really not meant to be confirmed. Okay, so one way or the other, all you can really do is say a hypothesis was, incorrect, or it was, or it's, the test went along with the hypothesis at least. Okay, so from there, you really have to worry about the engagement, and really, this really talks about, in the engagement, there's really 4 parts. There's observations and questions. There's hypothesis, predictions, and purposes. Okay, so obviously when we talk about observations, you're talking about using your senses. You can see things. You can hear things. What's that noise? You have a particular taste. That tastes really sweet. Why is that so sweet? And obviously, based on prior knowledge, you would say sugar, or you'd say maybe that's really sour. Why is that so sour? And of course, touch. Why does that feel maybe that way? And you can kind of work yourself through an observation that way. Eventually, you're going to ask a question about that observation. So why is that? You'll notice that something is really sweet tasting is your observation. Your question would be, what makes that so sweet? Okay, and you can ask any number of questions about a particular observation. But that's kind of the way you would start. Okay. Obviously, after that, you have to figure out, based on my question, so why is it so sweet? You can make a hypothesis, and it has to be testable. Okay, it can't be something off the wall, something that is not within the natural world. It has to actually literally be within the world that we know. Okay, can't be talking about a 5th dimensional being or something like that just because you want to create the dimension or something like that. It's not there. It has to be within this universe or this particular natural world that we know. So it has to be testable, but it has to be a suggested answer to the reason why, to your question. So for the most part, if I stick with the idea that my observation is something was sweet, my question is, why is that so sweet? My hypothesis could be, well, I believe there's sugar in this particular item that I'm tasting. Okay. After that, you can make any number of hypotheses about anything. This is an example of an observation of a flashlight not turning on, why the flashlight stopped working. We have 3 different hypotheses that we can talk about. We can talk about the batteries are dead. That's one hypothesis, answers the question. The light bulb is burnt out, another answer to the question. And maybe the switch on the flashlight is not working. So that particular hypothesis also works there. After that hypothesis, you want to go ahead and make a prediction. Predictions are always there basically to test for poor hypotheses and basically look at ones that, well, that really doesn't make a lot of sense, or based on what I already know, it should do this, and based on my hypothesis, it's really not following those rules. So it really helps eliminate poor hypotheses because there has to be some sound reasoning and it has to be testable. So if you can't test it within the natural world, that's what a prediction usually helps you do. But it's a if, then, because statement. Okay? If, then, because. So here's an example based on that first hypothesis we just saw. This is prediction number 1. If the batteries are replaced with new batteries, there's the if, then the flashlight will work and it will light up essentially. and the because the flashlight will now have a source of electricity to create a current to light the bulb. So that because should really be based on any prior knowledge that you have. If you have no prior knowledge, then your question is too specific. You have to back up a little bit further, and you have to ask more questions about what the actual item's doing. Okay. And here are a couple other predictions. Prediction 2, if the bulb is replaced, then the flashlight will work because the circuit of electricity will be complete, thus lighting the bulb. Okay, so those are examples of what we're talking about. This is the purpose. We do this a little bit more when we get to our own labs, per se. We give ourselves a purpose of what this is supposed to be doing. It's basically the same thing as a hypothesis or a prediction in a way, because we're trying to determine the relationship between two variables, but it really sets up what we're actually doing by putting our independent variable and our dependent variable together in one statement. Gives us something what this particular experiment is supposed to do. Okay. All right, so then we get into experimental design. This is very important. Of course, with any scientific endeavor, we want to try to control the environment in which it's in. If we have too many changing items within our experiment, it's not controlled. Thus, it's not a very good idea. So within our control experiments, we want to have only a single experimental variable. And of course, a variable is anything that really changes within the actual experiment. So we're looking for only one. So it compares, especially in social sciences and whatnot, especially when we talk about medicine or the medical field, they really like to have a control group and experimental groups when they talk about those things. And they'll see how a particular medicine might affect a greater number of individuals. So say a study of 100 people on an experimental drug versus 100 people not on that experimental drug. How do the results come out? And obviously, if it's a good drug, it'll be up towards 80% of the individuals saw some effects from this particular drug. Okay. So anyway, you have a control group, which is the normal standard for how something will happen. So these people have progressed with this disease. The experimental group, of course, is a group that gets this new medicine or this new therapy or whatnot, and this is how they recover or don't recover or whatnot. Okay, so that's kind of how control groups and experimental groups, and that's really for something that will have an effect on something else is done. Okay, now with that in mind, we want to make sure that we know what a variable is. First of all, you have to know that a variable is a condition that can differ within an experiment. In a controlled experiment, we want to try to control as many variables as possible. So when we do this, we have to keep as many things the same as we possibly can. We have two different types of variables that we test. Okay, the one that we are in complete control of is called the independent variable. Experimenter has complete control over that one. You're literally changing it. And then, of course, you have the dependent variable. This is the variable that will respond to what you're doing as you change the experiment. So if we go back to our flashlight example, if I change the batteries, that's my independent variable because I'm controlling that. Okay. My dependent variable would be whether the flashlight works. So it's really a reactionary type variable for the most part. Okay. When we analyze the data, of course, we want to make sure that we know we have two different types of data we can collect. We can collect quantitative data, which is measurements, okay, and qualitative data. So when we talk about the flashlight example, you're talking about a qualitative measurement because you're really not measuring how much light, you're just measuring that, oh, there is light. So it's a qualitative description, so whether it works or not is based on that. Okay, when we talk about this, you have data points. Now, it's something as simple as whether it lights or doesn't. You probably don't need a ton of data points. For the most part, it's a fairly simple experiment, design, thought process, or whatnot. When we talk about something that, when we're talking about a concept of how something works, we want to see multiple data points. This allows us to make a better description of how things work together, how variables work together. Okay, so basically data points are points at which data will be collected. So for, if you remember from last year, we had several data points where we would take an experiment Of course, we might measure how fast it's moving, an item is moving, and we kind of take different distances or different amounts of time and see how far they've gone, or different distances and see how much time it took to get there. Those are the different data points that we were referring to. Okay. Of course, drawing conclusions is basically all you want to try to do in science. You're trying to come to a basic conclusion. Analysis is the development of charts, graphs, models, whatever, to aid in the critical examination of an experiment. Even something as simple as a flashlight can even use a model, even in a description, to how it works. The idea that, of course, batteries hold a certain amount of electricity or electrons, stored electrons, and they'll move through a circuit is a critical way to explain how a flashlight works. So that model is important, but charts, graphs, and models are the two model the relationship between the two purposes. So a lot of times you'd say that putting these batteries in, greater charge in the batteries will go through the literal circuit, and this is the reason why the flashlight works now. Okay. Of course, there is always the conclusion or the final judgment. It's developed from the examination of those charts and graphs and saying, okay, well, this seems to work here. It seems like the data is telling us that yes, indeed, there is light at the end of the tunnel here, or sorry, not the end of the tunnel, the end of the flashlight. So this seems to be a proven way to make this flashlight work. Okay. So we can go ahead and talk about constructing theories, of course. Theories are really an explanation of some phenomenon, and it's based on an observation, experimentation, and reasoning. So it's not just a wild explanation that has no backing. So a theory really has to have many different parts, and it has to be supported by a large quantity of evidence. And it doesn't conflict with any existing experimental results or observations. So if you're just coming up with something and it conflicts with what's known in the world, it's not become a theory yet. Okay? Again, you have to have lots of evidence. A lot of people have to agree with you to make it become a theory. Okay? So that is kind of where we'd be, of course. But thank you very much for listening, and good luck.